Hello, welcome back. Today we will talk about diffusion. More specifically, diffusion, we will talk about Fick's first law. Now, we commonly call this steady state diffusion. Steady state diffusion, meaning the concentration gradient doesn't change with time. It is constant value, so you can simply write it as delta C divided by delta X. Now, people commonly think Fick's first law is only dealing with steady state diffusion scenario, but actually it is not. So this is a very general case, very general, very general case that doesn't care about time. This is actual definition of steady fixed first law. This is not wrong, and it also doesn't only deal with steady state cases. It deals with all cases. It's just that it doesn't really care about time. It doesn't see time as deal maker. You can put it like that. So basically, if delta c divided by delta x is a constant value, like in this case, then is steady state. When delta c divided by delta x is not equal to a constant value, then it is non-steady state, meaning the concentration gradient will change over time. But let's not get that deep into this, okay? Let's just today we'll only deal with steady state diffusion first to help you grasp this concept. Now, we all know this is the expression for steady state diffusion in x dimension. So it's a one-dimensional diffusion, this scenario, okay? So you can simply draw a diagram like this. So there are 2 points. You can think of this as a wall, okay? This wall. Now the concentration on this side of the wall is C1, and the concentration on this side of the wall is C2. Then the flux has a unit of gram divided by cm squared multiplied by second. This is the unit of flux. Will equal to minus d delta c divided by delta x. So you can easily see that this is the slope, right? Slope equal to delta c over delta x. And why is there a minus here? This is key point. Why minus? Well, of course, flux can't be a minus value, right? Flux mean that certain amount of vector or certain amount of field is going through certain area in certain amount of time. That's why it's gram per unit area per time, right? That is the physical meaning of flux. How many, okay, let me write it for you. Physical meaning. Number of atoms or molecules that pass through unit area in unit time. Now, flux can't be a minus value, but delta C over delta X, the concentration gradient. Now, in this gradient, now in this equation, you can clearly see that this gradient is a negative value, meaning this side has less amount of whatever this, let's say it's a boron atom, okay? Boron atom is diffusing through this wall. Now, concentration of boron on X2 side of the wall is much lower than X1, so the gradient should be negative. So basically, the meaning of diffusion is that, of course, it flow to area with lower concentration. That's the physical meaning. So if certain point has less material, then the material will flow towards that area. It's just that easy. Then this is negative term. This is plus term. This is just a constant. We call it diffusivity. Then, of course, it's a constant value, by the way. Then that's why you add this minus to match this positive value of flux. All right. So that's it. And why do we call it steady state? Meaning, let's focus on steady state, physical meaning. Meaning delta C over delta X is a constant. It doesn't change with time. So how do we achieve this? How do we achieve this while the boron atom is still flowing? How is that possible? Of course, it means that this concentration here, C1, stays C1. C1 will stay C1 even when time flows. This is the definition of steady state, that nothing will change over time. That is the definition. So how is that possible? Of course, it's very easy. So boron in equals boron out. At this wall, at this point, X1 point, materials will go in to this X2, but what goes in will equal to what goes out of this. So this is in, this is out. So it matches delta C at C1, at X1 is 0. So C1 is constant value over time. Same logic for any point in this system. We call that steady state. Therefore, delta C over delta X, as you can see in this diagram, should be a constant value. I'll mark this on next lectures with Fick's second law. All right, that's all for today. Thanks for watching.